So I'll just go with an introductions. So hi, this is Banu. So today I'm going to take the session on the RISC-V, which is a kindly demo session. So from here on, today I'll give you the brief idea about the RISC-V processor. So how this sessions will be held from here on, and this will be basically 6 weeks course. So we're gonna train you on the basic implementation of the RISC-V processor. We're gonna see the advantages of RISC-V and how the pipeline processor is implemented using Verilog. We're going to implement the hardware implementation. That's it. And here nothing involved in the computer organization or anything. So the basic understanding of the computer organization is much needed over here because uh, it is everything, right? So when designing the processor, computer is nothing but the processor, right? So before starting getting more into the RISC-V, I'm gonna say you what is RISC-V, right? So any of you guys know what is RISC-V before? Is there anyone, right? I've been asking you guys, is there anyone who knows the RISC-V processor before? Is there anyone who worked on the RISC-V processor?
No, sir.
Right? What?
No, sir.
Am I not really audible?
Sir, I think you are audible, sir.
Right. Okay. Someone is texting me I'm not audible. So, okay, now it is clear, right?
Yes,
My
sir. Now
voice is
it's,
too. Is my
sir,
voice
I
too
think,
low?
sir, I think so. It's trouble from his end. Actually, your voice is loud and clear. For me, I don't know about
Mhm.
others. If everyone responds means, yeah, on that time it will be easy to know. Is audible, sir.
Okay. Okay, then fine. Yeah. So I'm gonna start the session. It's a kind of demo session, so there is nothing more involved into the subject discussion or something like that. So today I'm gonna give you the brief idea how the lectures will be there and how the just overview about the RISC-V and how the classes will be taking. Yeah, right. So I'm gonna say you a few things about the RISC-V processor and so how it is originated, the history of the RISC-V. The RISC-V is the full form of the RISC is like a reduced instruction set computer. So the five indicates the prefix five indicates a five-stage pipeline, right? There will be the five stages of implementation in the processor. So which is basically the RISC-V. The whole computer is nothing but a processor which is implemented in the five stages. So this is the one was developed at the University of California, which is like in the California University, starting around 2010, 2010, and developed by Asanovic and David Patterson. These are the two persons who have taken the initiation uh, on the working on the RISC-V processor with the aim of creating an open source and a free instruction set architecture for the academic and commercial purpose. Their motto is to start the work on the processor. It's a kind of free source, open source in the sense it is clear to everyone. There is nothing, you don't need to pay anything for this. So they have designed the basic architecture for the instruction sets, and they have released that as a free thing, like a free thing available in the market. So that's the thing they have designed over there, and they asked, they were there will be a kind of flexibility of using that, and we're going to implement according to our customization. If we do have some kind of customizations by using that, the basics instruction set, we're going to build the customization, like a functionality with the specifications what we really needed. So with that specifications, we're going to use this conventional instruction set and implement the thing what we are actually aiming for. So And when they have started that, they do have some kind of motivations. What are the motivations? Are like they have open source, they just want it to be freely available for everyone. Those who are really enthusiastic in working on the processor design, and this openness allowed researchers and the developers and the companies to access and modify and implement the architecture freely without licensing fees or any restrictions, without any restrictions or without any license fees or anything. That's the main motto of the inventors of this RISC-V processor. So as it is available freely on the market, so it is like available to any uh, individual who really wants to work on the RISC-V processor. And can someone mute yourself? Like, who's that? And whereas coming to the RISC-V Foundation, I'm going to say a few things about the RISC-V Foundation. What is the main motto of the RISC-V Foundation? In the late 2015, I think, the RISC-V Foundation was established as a non-profitable organization. They don't want to make any business with this foundation, and they just want to make the knowledge, make each and every individual to gain knowledge on this foundation, the RISC processor, and to promote the standardized the RISC-V architecture, and by collaborating collaboration by conducting the collaborations among various companies, universities, and the individuals who are really interested in working on the risk processes, right? Whereas coming to the adoption and the growth, how, where it's been adopting, what I have already said, risk is everything. It's been growing in the recent years, right? So most of the recent companies has been really looking for the risk, working on the RISC-V processors. So recent years, RISC-V has gained traction in various domains like research and the embedded applications, basic embedded applications like microcontroller based applications. Even if you can see the washing machines in our household purposes, and the temperature monitoring devices and the humidity monitoring devices, air controllers, right? Air conditioners, sorry. So these all are the things we're gonna really implement using the RISC-V. So we're gonna adapt the RISC-V processor, and it's been growing rapidly uh, day to day life, right? And whereas coming to the ISA versions, um, you're gonna see what are the different flavors of what's the heck. So just listen. The ISA versions, we do have a 32-bit registers. In the processor implementation, we do have a few registers.
Just a
Um,
second. Whoever written this, can you remove that?
right, it's all right. Okay, okay, no problem. Like they've been new to this meeting, so it's okay. Uh, Guys, just pay attention to the lecture and listen to it. Okay, it's a very simple lecture, so it won't even be more than 40 to 50 minutes, right? So please pay your attention. It's a great step. You've been like really, there are 31, 32 people, just like one more person joined over here. So you've been taking good initiation, right? So it's a great thing. So you're gonna get some basic idea about the processor design and everything. So please pay your attention over here, right? Okay. And in the processor design, we do have a lots of things involved, the basic building blocks, and everything. The processor has some kind of storage in there, which is called register file. That register file have lots of flavors. With that, we can say that we do have ISA versions. So we do have a register file of 16-bit, 32-bit, 64, and 128. With that, lots of flexibility of having that much register weight. We do have lots of flexibility of using ISA versions. So I'm gonna explain you why we have this much flexibility in designing the registers. Why don't we go for the 16 or 32 or 64, 128? So why these many kind of bits are been using in the register register file designing, right? So I'm going to explain you that in the future slides, okay? And academic and industrial collaboration. So as the RISC-V has been gaining a lots of traction in the recent applications, it's been booming in every field, every industry. So it's been gaining a lots of impact, creating a lots of impact, so that the academic institutions and the universities and also the industries has been um, started collaborations on RISC-V processes, and also conducting great amount of researches on these academic and sorry, RISC-V processor, right? So these are the main motivations of the RISC-V processor design. When they have started, so they have already uh, they've been fascinated with all these things. So they have really sensed towards the future of RISC-V. So that's the reason they have started it as an open source. So uh, and the motivations are very clear over here, right? So uh, I'm gonna give you the idea. I have already told you, where the RISC-V is been booming, right? So uh, the RISC-V has been gaining a lots of significance in these the fields what I have mentioned over here. We've been using the RISC in the basic embedded applications, the household applications, as I have mentioned before, which is like washing machines and temperature control, everything. We're gonna we're going to use the microcontroller, which is based on the RISC processor. So we're going to implement the microcontroller based on the RISC principles, so that the microcontroller is designed, and based on that microcontroller, we're going to use design various embedded applications and the consumer electronics. The consumer electronics, such as examples like smartphones, tablets, and the smart TVs, and also few home appliances, because the consumer electronics are using the RISC because it has a lots of versatility, and which allows the manufacturers to customize the architecture to meet the specific performance and the power requirements. So for that, it's been using the RISC processor, to meet the specific uh, performance, the requirement in the performance and the power requirements. For that reason, we've been using the RISC-V processor. We're gonna have lots of flexibility in the performance, and also power consumption. It's gonna consume less power compared to any other processor, right? So, and whereas coming to the high performance computing in the sense, I'm gonna show you maybe when we are designing the instruction set architecture, I'm gonna explain you what is the high performance computing, because even if I say something about the high performance computing over here, how the calculations computations are being carried on the RISC-V processor, you may not able to aware of that things. So when we've been designing on the instruction set architecture, when the next lecture is on the instruction set architecture, so I'm going to explain you what is high performance computing. For now, I'm going to explain you that uh, why the base for complex computations and huge workloads, we're going to use this RISC-V processor to take on these nowadays the real time the real-time applications are too complex, right? We're gonna look into all the safety standards and the security standards. For that, there are the complex. They will be involved in the complex algorithms to solve that algorithms, and to get the solution for that problems. We have been using high performance computing devices. So where the in that devices also we've been using the RISC processor to take these to work on these workloads. And coming to the data centers and the servers, uh, as it is an open source available easily available to anyone, so data center operators to customize and operate their infrastructure for specific workloads, right? So to customize and optimize the infrastructure, what do they have already in there? So with the RISC, we're gonna customize everything. So we do have some basic customizations when with the open source. So when we come up with a few more enhancement to that, so if you want to enhance the basic design, so we do have to work a few things, not from the scratch. So there will be some scratch thing already available over there. With to the scratch thing, we have to add some enhancements so that the device gonna work for according to our requirements. So data centers and the servers are also been using the RISC-V processors, and the networking and the communication. Uh, Basically, the networking and the communication involves in the devices like uh, routers, networking equipment. You've been aware of the routers and the switches, right? And also other communication devices. So with these, we can also design. We need some basic kind of processor to work all these kind of electronic devices. So we're going to implement even no matter where we are starting. So even if it is a minute application, we can implement that using the RISC. And if it is too much complexity involved in that, so we're going to use that. You're going to use the RISC-V processor. So networking and the communication industry have also been using the RISC-V. So it's been also booming over there in that particular industry, and automotive systems. So whereas coming to the automotive systems, the main primary thing is like safety, right? The safety, and what's the other thing? What's the one most thing we've been expecting from the automotive systems? Comfort, right? So in terms of the comfort and the security and the safety, uh, suppose if there is an electric car or like any diesel car or any petrol car, so in that we've been expecting some kind of a safety standards. Like if the vehicle is very near to the, if the vehicle is going at suppose if it is going at 150 miles per hour, so if it applies a brake, even if it applies a brake, there might be a chances of hitting the car opposite to that car. So to prevent that from hitting to the next car, so we have to design the like ABS, right? You've been anti-braking system, right? So with that, like nowadays ABS been everywhere. So to make advancements in ABS or like ADAS, there will be one term I'm gonna say that advanced driver assistance systems, ADAS. Maybe you guys are aware of these things, ADAS. So which is like assistance. It's gonna assist you like if something, like suppose if you just want to go for 100 miles trip or something like that, if there is a fuel, some fuel inside your car, maybe or may not be your car, the fuel inside your fuel tank will be sufficient for that trip, so it's gonna guide you. So for that small application, it's a very basic thing. So we've been using the RISC processor, not only using for to indicate that small thing, we are using the RISC processor. There will be multiple things like even if you apply for autopilot system, so there will be autopilot system for that. It's gonna sense everything. Suppose if your device, if your car is going at 150 kilometers per hour, so if when it is in autopilot mode, so if the sensor senses a device, if sensor senses a one more car which is 1 meter apart from your car, so that time there might be a chances of hitting that car very badly, right? So the damage is gonna be very severe. So to prevent that, to prevent from hitting, so the processors are need to be worked. So to monitor the sensors and the braking system and the comfort system inside the car. So if the humidity inside the car is been more, so the temperature has to go low. So the temperature has to increase, right? So when the to control all these small things, we just need uh, the processor to take on everything. So to measure, to calculate everything accurately, and to operate everything accurately, we need a best processor. So to implement all these things, we need a basic processor which is already there at the scratch, which is called scratch in the sense of something which is already developed over there. And if we make some enhancements to that particular scratch processor, it's gonna work to according to our specifications. So that's the reason. Uh, risk is booming in automotive industry as well. So in the aerospace and defense, so every aerospace and the defense, which is the one going to represent the reputation of the country. Every country has been investing their per capita, like their even if you just consider the India, we've been investing crores and rupees on the aerospace and the defense because it's our reputation. So to take on the to just prevent the enemy missiles entering into our nation, so we have to prevent that missiles. For that, we need a good uh, electronic equipment to sense that one. We need a great sensors to work that sensors accurately. We need a master called processor to control all these small things, right? So for that, we can also implement using the RISC-V processor. RISC-V is also booming over there in that particular industry. If you really stepped into that uh, aerospace or defense, you're gonna really got to know how the RISC-V processor are really working over there. I'm gonna say, as I got the opportunity to say how the RISC-V processor have been implementing. So uh, in the aerospace or defense, in the space also been using this. So um, have you guys heard about the mission called Mars, Mission Mars, like a Mission Dangle? Have you heard of the movie called Mission Dangle? Which is like we have sent something onto the Mars planet, right? So, which is very successful project we've been implemented. For that, India got a very good reputation, isn't it? So, in the initial days, when the rover lands on the Mars, the Pathfinder is there. So, for that Pathfinder, it's been working initially very good, and when the days been on progressing, so the Pathfinder program crashes over there, and there the bug hits the program. So, what happens over there is like the microcontroller stops functioning. So microcontroller is nothing but the RISC processor or any other processor, any bloody processor, right? So it's been stopped working over there. So uh, guys, are you listening? Am I audible?
Yes, sir.
Yes,
Yes,
sir.
sir.
Okay, yeah, that's good. Yeah, spot on, mate. So uh, like the Pathfinder has been crashed. The program for the Pathfinder has been crashed, and the maybe few bugs has been erased over there. So the microcontroller is not responding properly. So there will be one watchdog timer is there. So the watchdog timer is the one who gonna sense all the uh, uh, who gonna sense the microcontroller all the time. It has to sense for every duration of time period. Like there will be some time period duration. Within that time period duration, if the microcontroller fails to send signal to that watchdog timer, it gonna reset the microcontroller and sends the signal to the remote area, like to the Mars, which is like from the Mars to the planet where we are living, which is almost 40 million miles away from the Earth, right? The Mars is 40 million kilometers away from the Earth. So, like the watchdog timers has to send the signal like the program has been crashed, so the microcontroller is not working properly. So needs to repair that as soon as possible. So to put that pathfinder on the proper track, so it has to function. It has to work on that. So for that reason, like they've been like why how these kind of things have been like how we the communication has been happening. It's not a simple thing, isn't it? 40,000 million miles or million kilometers, whatever it might be. How the communication have been happening between the Mars and the Earth? How do we came to know that the rover has been landed on the Mars? How all these things are being we've been noticing. So that's where the processor comes into the picture. So this is what the processors are doing. So uh, how it is doing all these things. So this is about we gonna witness that in the future things and like how we are implementing. We are not here to something like that. We are just here to implement RV32, RISC-V 32-bit integer instructions. We're going to implement that, whereas the 39 instructions are there. So 39 different flavors of instructions are there. We're going to implement our instruction set architecture according to that 39 instructions. So we have to be clear that these 39 instructions are working properly on the structure what we have designed or not. That's it. So um, we're going to implement that RISC-V processor on FPG and the ASIC designs. Uh, as you guys are more involved in the semiconductor industry, you may aware of FPG and the ASIC design. What is that FPG designs and the ASIC designs? Field programmable gate array and application specific integrated circuits. You guys may be known this one. And the custom designs is the one I'm going to say you this because the custom designs are nothing but as there is a scratch processor which is already built by the two persons who I have mentioned before. So they have already designed the basic processor, right? So they have designed the architecture for some kind of a 32-bit or something, whatever it might be. Suppose one of the guy who been responding for me for regularly. So I'm gonna pick one person. Okay, Deekshit. I'm gonna say Deekshit over here. So he's the one just want to design something which is really which is a great application. He do have some kind of specification in his mind, so he gonna design that into he gonna design a processor to implement that specification. Suppose he just want to design some basic application like smart gardening smart garden monitoring equipment. Suppose if there is some kind of plants are there in your garden, based upon the temperature and the humidity, you have to feed water to your plants. So you do come up with that specific requirements and the functionality and the specifications, everything he got, and he just want to design some kind of processor to work on that. So it's a kind of a very basic household application. So we have to design a very small microcontroller. So he came up with that specification. So he needed a processor to design that. So to design the processor, what he has to know, what's the prerequisites he has to know, what's the basic prior knowledge he just have to know. He have to know what is processor and how the processor have to implement what the basic things I just really want to apply, right? So he need the conventional knowledge of the processor, right? So guys, the session gonna finish in 1.5 minutes. So if it is finished, uh, you have to join that using the same link. So till the time I'm gonna say something. So when you do have some kind of specifications, uh, so you have to make that the specification has to work, implement that on the available instruction set architecture. So you have to make use of the conventional instruction set architecture and have to work that instruction architecture for the specifications what you have demanded. So that's the thing what we have flexibility in designing the customization of designs, right? So less than 1 minute soon after finishing this session, uh, I'll request you guys to join to another session using the same link, huh? Yeah. So the RISC-V. So the risk in the sense, the name itself saying that reduced instruction set computer architecture, right? It's a computer, reduced instruction set computer. So why I'm getting resonance here? So uh, so when I'm speaking, so if someone is asking the doubts, right? So when I'm speaking, when you're listening, can you please turn off your mic? Huh? Okay, thank you very much. So the name itself indicates that reduced instruction set computer. It's a computer. Computer is nothing but the processor. It's a heart, it's a brain, everything. So, and in to the converse, so when you have in the coin, when you have head, there will be tails, isn't it? So there will be opposite side is also there, cis. which is like a complex instruction set computer. So for now, you have asked me like, is there any other set of anything, other kind of computer like this? So there is one. I'm going to say you that. I'm going to show you the differentiation between the RISC and the CIS in the future slides, maybe in the next slide, right? So wait till that time. Okay. I hope you
Uh,
got it. Who is that?
Sir,
Yeah.
Dikshit, sir, this is Dikshit. Sir, I mean,
Yeah.
like, sir, for aerospace and the defense, or like if we are sending some outer space means, like, we
Mhm.
want some, uh, like military grade
Yeah. 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 Okay. Yeah.
certificate.
Yeah.
So,
Yeah.
is that kind of I'm asking?
Okay, just listen. Like there will be some privilege modes are there. Okay, privileges are like uh, Dixit. Like there will be some privileges are there. Privileges in the sense like some kind of what how to say that scheduling. Okay, suppose first. So listen. Uh, how to say this? If something is like if you want to specify as it is a military graded processors are like as you come up with op amp, there will be two grades are there. One is like a user mode and the other one is military grade. So for the general applications and the basic applications, we're going to use the user mode op amps, and for the military grade applications when the complex in calculations and the mathematical more complex things involved in designing or something like that, we're going to use the military grade things. So um, there will be few things like that. There will be three privileges are there. So for the basic microcontroller applications, we going sorry what? What you said? Sorry. Hello.
No, sir, I didn't tell anything.
So someone is saying something. So that's the reason I have stopped. Okay, it's all right.
No, sir. Someone has on the mic so that it was, I mean, distorting the voice.
Yeah, yeah, yeah. Thank you, Roshan. Yeah. Okay. There will be some kind of privilege levels are there when you are come up with some kind of specification. So for that specification only, it has to work. Because as a hardware design engineers, we do have to keep one thing in our brain, that is like there must be some kind of reusability, right? So when you've been using something for that specific thing, it has to work, and when some kind of additional software we do install into the hardware, it has to operate for that also. So that's what we have been saying, the reusability. So um, as a, as a semiconductor industry, we all the people are there in the semiconductor industry. So who is the father of our industry? Like a Moore, Gordon Moore is the father of our industry, right? So he been saying like he has given one statement which is like a rule or law, which states that for every 2 years or for every 1 year, the transistors on the chips gonna double by every year. So it's almost reached to the saturation level, right? So we have to concentrate more on the physics other than doubling the number of transistors on the chip. We have to more concentrate on the physics, right? Now the big semiconductor companies like a Samsung and the Intel is still there at 7 nanometer node technology, I think, but the Samsung has been advanced to 3 nanometer technology, and the Texas Instruments and then some other few companies are there. They've been more concentrating into minimizing the node to 3 nanometer technology. Beyond that, there will be a lots of opposition from the physics. So uh, we have to utilize the hardware which is already there. So reutilization, so reusability or something like that, we have to concentrate more on that instead of doubling the transistors on the chip, right? So based upon the application, right? Uh, Okay. So based upon the applications, if you guys are designing for RV32Y base integer application, I mean, instructions, so there will be some kind of instructions like R to R, J type, immediate type. These kind of instructions are there,
Sir,
right?
excuse me, sir. Sir, can you please mute Aman? Like you are the host, no? So you can mute Aman.
Who
Like
is he? Is he making the noise?
like he switched on the mic, so only. Yeah. Now he switched off, so only.
Okay, Aman,
He
just take care
was
of yourself, yeah. So, Dikshit, I'm gonna say something. So you're gonna get the things in the future. So we've been wasting lots of time over that. So
okay, sir. Okay, sir.
just pay with me for some time. I'm gonna clear you that. Okay.
Okay, sir.
Where we have stopped before. So I'm gonna share you my screen. Mm, so can you guys able to see my screen?
Yes, sir.
So as I have already told you, the other side of the coin, contraposition, which is like when you are working on something called RISC, there will be some other side also there, which is called CISC, which is like how to say that it is a complex instruction set computer. So uh, I'm going to explain you the basic differences between these two things. Uh, in terms of the hardware, there might be some similarities of designing the hardware and the implementation, but the philosophy and execution methodology might be changed. Whereas instruction set is everything. I have told you that before. So instruction set complexity. I'm going to say you that how the CISC involves. The CISC processors have a large and complex instruction set with a variety of instructions that can perform multiple operations in a single instruction. Okay, so within the single instruction, it's gonna perform the very big complex instructions, right? So the very big instructions in the sense instruction might vary in the length. Some might be very big, and some might be very small. So even though if it is big, it may take only one clock cycle to execute that, and if it is some of them are very small, maybe it demands for more number of clock cycles. So there will be no fixed length of the instruction length. So there will be of different lengths on instructions. So in terms of the instruction set, the CISC process with the different lengths in the instructions. Whereas coming to the RISC, there will be some kind of a fixed length, fixed instruction format. If it is a 32-bit format, 32-bit register file you've been designing on and you've been working on it, the instruction length will be the 32-bit. Every instruction is of 32-bit. If it is 64, the instruction length will be 64. That should be it works like, okay? So whereas coming instruction set complexity, you may be clear with that thing. So in the CISC, in the CISC thing, there will be of a different lengths in the instructions. And whereas coming to the RISC, the each and every instruction is of a same length. So coming to the execution philosophy, the CISC processors are designed with the philosophy of providing powerful and feature-rich instructions which can handle the complex task in a single operation. So no matter how complexity involved over there in the CISC instructions, if the CISC instruction itself involves in the more complexity, if it is being I'm gonna say you where we've been deployed this CISC processor. The basically Intel processors are called CISC processors. Okay, Intel processors are the CISC one, and the RISC are like your smartphones, which is designed and customized by the ARM. Have you heard about ARM processor before?
Sir, like ARM Cortex.
Yeah, that's it. They are like basic and microcontrollers. ARM Cortex are like microcontroller fine things, right? So I heard about the Snapdragon
Yes, sir,
Qualcomm.
Snapdragon.
Qualcomm produces the Snapdragon processor. Heard of it, right? So what do they do basically? Do they customize the processor on their own, or like do they get help from any other vendors? Who gonna help them? So the ARM gonna help them. So ARM is the one who gonna provide some protocols over there, how the processor they just come up with some kind of node technology, like they'll just we wanna design this in the 7 nanometer technology or like 3 nanometer technology. They're gonna specify that. Who? The Qualcomm gonna specify that to the ARM. So we do have transistor limitations of this much, right? So we wanna use the 40 billion transistors on the SoC, and with that limitations and seven what's the latest processor that we are designing nowadays? What's the latest processor that's been running on your smartphones? I really don't know what's the processor being using. It's around the 900 something like that. I really don't know because I've been using A16. So okay, it's all right.
Sir, like
So in this
5G, triple eight, 5G, sir.
Okay, it's a 888 processor in the Snapdragon, Qualcomm Snapdragon, isn't it? So in that processor, uh, what they're gonna say some specifications to the ARM Advanced RISC Machine. The company called ARM is Advanced RISC Machine. They're gonna say that these specification, they're gonna come up with these specification. As I have told you before, here the Qualcomm is a Dixit. Suppose I am the arm, you're gonna come to me and have come up with some kind of specifications you've been demanding for this processor. So for that processor, so I have to design the processor for him, right? So I have to take the whole responsibility, the software updates and the hardware complexity. Everything I do have to take care of all these things and have to provide the processor within the submitted deadline, right? So this is the time which the risk and risk involves. Okay, so the risk is called the I'm gonna use the risk machine, advanced risk machine, right? The name itself, the name of the company ARM, R indicates the risk, and they've been using the risk machine for designing these small things, small instruction execution. So you got it right, where we've been using the risk and we've been using the CISC. So whereas coming to the execution philosophy, uh, the CISC processors are designed with the philosophy of providing powerful and rich instructions, feature-rich instructions that can handle complex tasks in a single operation. As I have told you before, no matter how long it is, no matter how complex it is, so it has to execute within a single operation. That's it. So for the RISC machine, it will break down the complex instruction into small instruction, and in each every single operation, it's gonna perform each and every small instruction. So single operation in the sense, the whole time period taken by the instruction to be executed. So within that time duration, uh, the processor has to consume a lots of power, right? So it may take several seconds to execute that instruction, right? So for that, what the risk is doing, it's been breaking down the complex thing into the reduced instructions. So in every instruction, in every operation, it's been performing one thing, one instruction, second, third, fourth, fifth, like that. It's been breaking down the things and been executing very faster than the CISC, isn't it? So compared to the SAYS, it's been implementing the things faster. It's been breaking down the complex things into smaller things and been implementing in a fast and speed way, right? So that's the execution philosophy where comes to the risk and the SAYS. You may got it right, how the instructions are executed. So he's like the big man who gonna take care of the big instructions. So he's the one who gonna take care of small. He will break down into the small things and will execute accordingly. So he's responsible for very complex applications like a MATLAB. Have you heard about the MATLAB in your undergraduation? So if you wanna execute, if you wanna run something on the MATLAB or Simulink or something like that, some EDA tools or like a very for that quarter prime, some that kind of EDA tools. For example, where I'm saying For example, these applications, if you want to run into the smartphone, the RISC processor are not able to handle that application. If you want to run that in the CISC, like any processor, Intel, AMD, Ryzen, anything, if you want to run that, what the applications I have told before, the CISC gonna take care of that and gonna implement it very easily. So for the complex things, it will be using the CISC. For the small break, for the mobile applications, what you've been using, the RISC is the best thing. So even no matter iPhone is also using the RISC thing. So RISC has a great demand nowadays. So here the RISC is the boss for us. Okay, don't underestimate the RISC. He's the boss for us. So coming to the complexity of hardware, uh, the CISC processors involved, like I've been taking on the more complex instructions. So it requires a complex hardware, isn't it? So when it's been taking on the complex instructions and all, so it demands a huge hardware to take on. For that, it demands a great hardware to decode and execute the various complex instructions, and also which leads to chip complexity, isn't it? So if the RISC processor is demanding for 40 billion instructions, and it may demand double or triple or more than that, the CISC, because it's been taking on the complex instructions, right? So whereas uh, complexity, CISC involves in the more complexity than the RISC. You got it right. So coming to the memory access, uh, memory access in the sense we do store all our instructions and data in the memory. So there will be some kind of differentiation how the processors are accessing the memory, how soon they're accessing. Like CISC processor instructions often involve more memory access directly. So CISC processor will take the instructions directly from the memory. That is like you're gonna come up with the instructions like load and store in the future videos, feature slides. I'm going to explain you how what is the load and store everything. So for that load and store, it has to access directly to the memory, CISC. Whereas coming to the RISC processor, increase use of registers. We do have registers, right? In the CISC processor, there might be or may not be the registers, but in the RISC processor, we do have registers. The register is going to take care of storing the data temporarily. Suppose if you do have a 16 GB RAM, which is like a which stores how I'm going to say you how the RISC processor or any processor going to do. You do got 1 TB memory of SSD. So you do have a solid state drive memory, 1 TB, 1 terabyte. In that, some 10,000 applications are there, maybe, right? So if you just want to pull one application and if you just want to run some YouTube in your CISC machine, which is like your laptop or any other complex device, so the time it's going to pull that particular binary data equivalent from the binary equivalent in the sense machine stores everything in zeros and ones, isn't it? Instructions and the data will be stored in zeros and ones. So it's going to pull that binary zeros and ones of that particular YouTube or any other application. It's going to pull that thing and put that into where it will put into the RAM. So the binary equivalent of particular application will be stored into the RAM. So the processor going to access RAM regularly. The processor has come up with the program counter, which points to the initial address of the instruction to be executed. So I mean more involving into the designing of the hardware. So the memory access for the registers, for the RISC machine, there will be the registers. So there is no need to access the RAM. There is no need to access the RAM all the time. So there will be RAM is the thing, small thing. We've been designing the RAM just to make differentiation between like something the processor wants. So it has to get the thing from the main memory, 1 TB SSD. So 1 TB SSD itself is a big thing. Maybe it's a kind of like the big metropolitan city. If you want to find someone in the metropolitan city, how hard it is. So if it is a small village, maybe it will take very less time to find that person, isn't it? So Suppose the metropolitan city is a big 1 TB SSD. Uh, if you pull the one binary equivalent of one binary equivalent data of one particular application, if you put that into the RAM, so for that processor, it will be very easy to find the addresses and everything in that small particular area. So it will access each and every address. Okay, if it hits the right address, so it will pull the data and put into the registers and perform some specific operation between the registers and write the data back into the registers, or like put the data back into the memory from where it has been taken, right? So it should be done over there. So uh, in terms of the memory access, the RISC has a very three kinds of memory. One is the register file, and the other one is the secondary memory, which is like a RAM, and the third one is the main memory. The main memory is nothing over here because it just stores that it simply stores the data. It's a kind of kiddie bank. It just simply stores the money, kiddie bank, right? So it simply stores the data and instructions, everything over there. And when you just ask your operating system to put the binary equivalent of that particular application, the process OS gonna pull that binary equivalent and put that into the RAM. So the RAM and the processor gonna take care of everything from there on, right? So the memory access is that, and whereas coming to the performance and efficiency, the last thing, uh, the CISC processors are suitable for the tasks that benefit from complex instructions and need fewer lines of code to accomplish certain operations. And they might be more efficient in specific application, which are also like complex operations are in common, right? So whereas in the the RISC processor excels in applications that require high performance and simple instructions that are to be executed well, that they are very particularly well suited for the task with repetitive operations and the data processing. Okay, so uh, to perform the complex things, we go for the SACE. If the complexity is more, if we can able to break down the complexity into small pieces of instructions, then we go for the RISC. Some kind of applications are there. No matter how complex it has to be executed in one single operation, right? So the time will go for the sales. So I don't care about I don't care about how many operations are there, but it has to be executed within less number of time, with less amount of time. Then I'll go for the risk. So in terms of the performance and efficiency, the risk and the CISC process like this. So this is the uh, overall view about the RISC processor. Maybe you got some idea about the RISC processor. And this is not really enough to get into the designing of the RISC processor. So I'm going to give you a basic understanding of the processor, few more things about the processor in the next lecture. So from here on, I'm going to explain you what is the course objective and motivation. So as you guys familiar with some things, basically the basic stuff in your bachelor's, and you are really passionate about VLSI, so you might be equipped with some kind of basic stuff within your skill set, isn't it? So the course objectives are like RTL implementation of the RISC processor, and is to design and create hardware implementation of the RISC processor using RTL design techniques. RTL design techniques in the sense, uh, what's the RTL design techniques? Do you know that? Gate level modeling. Yeah, there are few abstracts over there. So within that abstracts, we'll go for a structural designing, right? So gate level modeling, so these kinds of things are there. RTL designing techniques are that. So within that, we'll choose one thing, right? We'll go with that. And also the primary goals of the project are like a functional correctness. So like the design processor is working for the function, whether it is working for all the functions what we have basically intended to work on, whether it is working for that or not, and the performance are also we're gonna verify that. And whereas the verification, so if you guys are like more involved in learning the system verilog, if you really want to learn the system verilog, or like if you possessed with the system verilog in your skill set, so we're gonna write some few kind of test benches in using system verilog. So we do have a system verilog test bench architecture for the RISC processor. So I have seen many people have been saying that they do have some basic knowledge on the risk. Sorry, it's not about the risk. Verilog and all. So that should be that is a very fair enough for to this level of implementation. So if anyone is really interested in writing the test benches for the risk process, we'll take furthermore we'll dig more into that. So for my agenda over here is like writing the test benches using the Verilog and expandability. It's the main thing. So we're gonna write RV32I 13 for 32I in the sense base integer 32 2-bit integer instructions. We're gonna write for that, and we have 39 applications, 39 instructions. So the designed hardware has to work beyond that level, right? So there will be uh, jigsaw, some control signals are there, okay? Some flags are there. So to for the design what we have implemented by making by adding some more hardware, we have to uh, make sure that the design has to work for a few other applications like division, multiplication. Other than that, E-type, I have told you that RV32E. Before I have told you I, there will be some extensions are there. E in the sense extensions, floating, precision, double precision, all these kind of things we're gonna implement. Like we have to make sure that our designed processor also have to work for that things. Few things like if you have for design for 39 instructions, no matter from where it is hitting the other instruction out of these 39 one instruction may gonna hit from outside. So you have to be very thorough about your design so that your design also work for that particular instruction which gonna hit from outside the 39 instructions, right? So that's we're gonna concentrate into that. And I'm gonna say you the course outline. So the course, as I have already mentioned you that this is a 6 weeks course. I have already told her that this is a very small course, 6 weeks course. So we do have in the week one, I'm going to explain you the basic understanding of the processor design. So within these 10 minutes, I'm going to conclude the session. Basic understanding of the processor design. There, it involves in the computer architecture. How architecture in the sense that there will be two methodologies out there: Van Neumann designing, Van Neumann architecture, and hardware architecture are there in the computer design. I'm gonna make you through, walk you through all these things. What is a Van Neumann methodology or like architecture, and what is hardware architecture. So uh, I'm going to say you how the instructions are taken from the memory and how the processor execute the things. So it should be a basic demo on that processor design. So in the week two, uh, within this week, I'm going to finish this first thing. And in the week two, uh, risk risk instruction set architecture. So we're going to look into more into the risk instruction set architecture. What are the building blocks of the architecture? So what are the instructions we really working on, like R type, I type, J type, jump, register type, immediate type, jump type, branch type. Okay, these kind of instructions are there. So I'm going to explain you over there how we're going to implement for the R type instruction, how the hardware it should be, for J type, how it should be, for branch, how it should be. Like that, it should be done. And assembly code of risk and pipelining concepts. So assembly code in the sense, um, you have been writing software in high level language. For the software, what you've been writing, inside the communication should be done in the assembly language. One second, guys. So uh, you're gonna see that how inside the communication between the peripherals is gonna happen in the machine language, which is like zeros and ones. So how the assembly language, how the high level language is converted into the assembly code, and how these assembly codes are converted into executable files, and how these executable files are converted into object files, which is like a zeros and ones, and how these gonna store in the memory, and how these things are like will be with these things, how the processor communicate with the peripherals, external peripherals, and everything. I'm gonna say that through assembly code of the RISC and the pipelining concepts, which is a very major thing. The in the name of the project we have itself mentioned, like it's a pipeline project, right? So in the pipelining, I'm gonna explain you. Like if the processor is executing one instruction, and what if the processor hits with the other instruction, so it has to be taken inside the processor. And if the processor makes the second instruction to wait for some time, so there will be duration of a long time between the instructions execution. So which is like not favorable, like which is not desirable, isn't it, right? Huh? So how the pipeline gonna kill these processes, and how it gonna execute the things in parallel way. So I'm gonna explain you pipelining over there in the week 3. And in the week 4, when you are strong with the instruction set architecture and the assembly code of the RISC and the pipelining concept, we're gonna design the RTL design for the non-pipeline processor. Like without using the pipeline concept discussed in the week 3, we're going to design the non-pipeline RTL for the RISC processor. So we're going to check how latency is over there, like how much time it is taking to execute. Suppose if we come up with 6 instructions, if it consumes some kind of some number of cycles or some time, some kind of nanoseconds or something like that to execute these small instructions. So in the non-pipeline processor, it may take some random time, and in the pipeline processor, it may take some other time. We're going to differentiate between these two timings. Do you really get that? Is there any really, are we really getting the benefit from using the real pipeline processor or not? So this is the other thing we're going to witness in the week 4. Sorry, in the week 5, we're going to see that pipeline implementation of the RISC-V processor. So there will be the RISC pipeline implementation of RISC processor in the week 5. And in the week 6, we're going to write the test benches to validate. So in the week 6, we're going to see for the non-pipeline processor, we're going to write few test benches. And also we're going to write that that particular test benches, in the sense we do have some instructions. We're going to feed that instructions. We're going to put that instructions as a stimulus to the RTLs what we have written over there. So how for the same test bench, how both pipeline and non-pipeline processor are responding, how long will it take to execute the how long will it take by the non-pipeline processor to execute the same instruction, and how long will it take by the pipeline processor to execute that particular instruction. So we're gonna note down the time duration for the execution of the instructions, and we're gonna differentiate between these two timings. So within these 6 weeks of period, we want to finish this project. And I'm going to say you something. The prerequisites required for the project is like some kind of basic stuff required, which is like if you are really good at doing combinational and sequential logic circuits like muxes, decoders, everything. That's it. And the sequential in the sense D flip-flops. Other than that, nothing is required. Okay. So hardware description language, like if you are really good at writing Verilog or PHDL, it would be fine. No need of system Verilog. As in this level, there is no need of system Verilog. Verilog is fine. So if you have a basic understanding of the programming language like C is a software language. So with this, and also good understanding of the computer architecture. So I'm going to cover all these things in the future slides, in the future lectures. So that's it. These are the prerequisites somehow. If it is there, if it is possessed in your skill set, that's fine. If it is not, then no need to worry about that. We're going to cover that. Okay. So coming to the classes, there will be the classes on Saturday, Sunday, and Monday, because we do have folks. We do have to go to our work site. So from Monday, it's fine for me, but and the rest of the days I do have work. So and also you are available on Saturday and Sunday, and every day I'm gonna take 2 hours of a session. So in that session, you will be respected to ask doubts during the sessions, and also welcome to ask the doubts in the WhatsApp groups. Okay.
Hello, sir.
Yeah.
Okay, so in the whole course, we are going to write the RTL code of each block, right? Like program counter, decoder, memory, ALU, like this. And at the end, we are combining in the top level module, right?
May I
And
know
we are
your
going to
name?
verify, and we are going to verify through test bench also, right?
Yeah, right. Basically, one thing. May I know your name?
Sandeep.
Oh, Sandeep. Yeah, come on.
Huh.
You've been asking like if, yeah, we've been yeah, we're gonna write some RTL design for each and every building block. So they involve instruction register files are there, and control logic
Mhm.
is there, data path is there. So what's that? Muxes are
Decoder,
there,
Maxis, yes.
and program counter is there. So for each and every building block, we're gonna write all these things, right?
So
RTL.
you are going, so you are going to write the code in front of us, right? Or you have already written the code. Like how we are going to show us this?
What if I ask you to write the code? Like if I do, like if I explain how the program counter has been working. So
Mhm.
yeah, I'm gonna provide you the code. Don't need to worry about that. So what I wanna say you like first of all, if the class is on the Saturday, if I'm gonna take class on the Saturday, we do have classes on Sunday and Monday as well, right? So I'm gonna say you the specifications of the program. Suppose if you wanna designing the program counter, so I'm gonna say you from where the address has that how many bits address it has to strike, and what are the specifications of the program counter. I'm going to say everything to you. So I'm going to tell you the logic behind the program counter. I'm going to explain you everything. So I'll ask you to
Mhm.
write that code in the evening. You
Mhm.
just have to spend some amount of time on it and write some code. So if you are able to synthesize that one, if you're going to get the netlist from that, what the code you have written from there, if it is
Mhm.
meeting the specifications what you have designed, then it's fine. So in the next lecture I'm going to explain you if some people may not be no like may not be able to write the code. So the time we have to help them, right? So I'm going to provide you the code in the next second class. In the
Okay,
first
okay,
class I'm
understood.
going to say you. Yeah.
I think session time is over.